All right, so we're going to talk about study outcomes and power. So when you get a result from a study, you reject the null or you fail to reject the null. We're going to be talking about that today, what that means, and how we get those results and how often we get those results and what we can do more to get a reject the null result. That's power. So here we go. So this is the sampling distribution of the mean when the null hypothesis is true. When the null hypothesis is true, the two population means are exactly the same. And remember, we have that assumption that the variance is also the same for both groups. So really, when the null hypothesis is true, it's like one distribution is sitting right on top of the other distribution. You can't tell them apart. Population means are same, variances are same. And remember, the null hypothesis has to do with the two mu's being exactly the same in a two-tailed test. So the two mu's are the same, variance is the same. When null hypothesis is false, the two mu's are not the same. They're different from one another. So here is mu1, and this is mu1's distribution, and this is mu2, and this is mu2's distribution, and you can see the two mu's are separated from one another. Mu2 is higher than mu1. The variances are the same, so these distributions are spread out exactly in the same way, but the means are different. So we got these two situations going on. We also have, so we have two possibilities. Could be that the null hypothesis is true. Could be that the null hypothesis is false. We don't know which one of those is the case. What we do know is when we run the study, we either reject the null or we fail to reject the null. If we reject something that is true, if I tell you something is true and you reject it, you have just made a mistake in your judgment. If we reject a true null, we've made a mistake. This is called rejecting a true null, and it's a mistake. If we fail to reject a true null, so I tell you something that's true and you don't reject that, well, that's no mistake. You've made a correct decision. If the null hypothesis is false and the means really are separate from one another, and you reject the null hypothesis that says that the means are the same, hey, you've done a great job. If the null hypothesis is false, but you failed to reject it, you missed it. You missed that the means are different from one another, the mu's are different from one another, and you've made a mistake. So let's look. So we have two ways to make a mistake. We can reject a true null, or we can fail to reject a false null. And we have two ways to make a correct decision. We can fail to reject a null that is true, and we can reject a null that is false. And we're going to talk about the probabilities of these mistakes and how to keep from making them. If we make a mistake by rejecting the null hypothesis when it's true, we're going to call that a type 1 error. These statisticians, they don't have a lot of cleverness about them. They just go, oh yeah, that's an error. What kind of error? Well, that's the first type of error. Okay, so type 1 error. If we fail to reject a null when it's false, that's going to be called a type 2 error, and there are probabilities associated with these errors. So rejecting a true null, so the null hypothesis is true. There really are no differences between population means, but we reject the null. Falsely so. When we make that kind of an error, the probability of us doing that is called alpha. So alpha is the size of the critical region, and is also the probability of rejecting a true null. It's also the probability of making a type 1 error, because a type 1 error is rejecting a true null. If we fail to reject a false null, that's called a type 2 error, and the probability of a type 2 error is called beta. So we have alpha, an error of the first type, the probability is alpha. Beta, an error of the second type, the probability is beta. If we take beta and find the rest of the probability space, so 1 minus beta, we get what we call power. Power is the ability to have two separate mu's. So the null hypothesis is false. And to detect that in our analysis, so rejecting the null hypothesis when the null hypothesis is false, that's power. So if there are differences, between the population means, my ability to detect those differences in my analysis, that's called power. I want a lot of power, which will minimize beta, and I want to minimize type 1 error. So I have two things going on. I want to minimize this and maximize this. So let's talk about alpha, because that's the easy one. If the null hypothesis is true and these two means are exactly the same, the probability of me rejecting the null, so I'd make a mistake doing it, but the probability of me rejecting the null is alpha. And the reason it's alpha is because when these two means are the same, I have to cut this distribution somewhere, the sampling distribution. I have to cut, because otherwise this distribution goes to plus and minus infinity. Well, so all the mean differences are in there. All the means are in there. So I have to cut this distribution. I'm going to cut it in a way that minimizes the amount of space that I'm cutting out and calling different from my region of non-rejection. But I still have to cut. The area under here, the number of means that I find under here, the proportion of means under here. If I grab one of these means and compare it to mu for one of these two groups, I'm going to reject the null. But I'm only ever going to reject the null if I grab a mean, a sample mean from over here or from over here. So if alpha is 0.05 and this is 0.025 and that's 0.025, I only have a 5% chance of grabbing a mean over here or grabbing a mean over here and rejecting the null falsely and making a mistake that's called type 1 error. So alpha is the probability of making a type 1 error. Now I can, if I use 0.05, I take a 5% chance of making a type 1 error. But I can also, instead of using 0.05, I can set 0.01 as my alpha level and only ever take a 1% chance of making a type 1 error. But like I said before, a lot of times most people use 0.05 most of the time, and we're going to figure out why that is when we talk about power. So, when the sampling distribution of the mean is false, we have a lot going on. So what I want you to recognize right here is that, okay, these are two different distributions. This is mu2, this is the second distribution, this is the first distribution. Here's the difference between mu1 and mu2. Here's the critical value for this distribution over here. Any mean that I get, now these means over here, I don't know, if I had a mean right here, I wouldn't know whether it came from this distribution or this distribution because they're similar right there. There's slop, I call it slop. They slop over one another. But if I get a mean out here past this critical value from distribution 2, a sample mean, and I compare it to mu from distribution 1, I'll reject the null every time because it's beyond the critical value. And this distribution looks like more than half of it is beyond the critical value. So I have more than a 50% chance. I probably have a 60% chance of rejecting the null in this case because most of the distribution, like maybe 60% or so of it, is beyond that critical value. So when I pull a mean, just randomly pull a mean, I'm likely to get a mean from this side, more likely than I am to get a mean from this side. So I'm more likely to reject the null than not, the way these are set up right here. Okay, anything in red, anything in this distribution 2 that's beyond this critical value, it gives me power. The area beyond this critical value, all of this over here, gives me power to reject a false null, to reject the null when the mu's really are separate from one another. I want as much power as I can get because I'm doing these studies to detect differences for the most part. I think there's probably a difference, and I want to detect that if it exists. So we're going to talk about who or what controls alpha. Well, that's easy because I just told you, you can set your alpha level to 0.05, you can set your alpha level to 0.01. It's you that controls alpha. It's the researcher, the experimenter, who determines alpha. So you determine the chance you're willing to take to make a type 1 error. So you can take a 5% chance, you can take a 1% chance. The rules are you can't take any more than a 5% chance. You can take less than a 1% chance, but most people pick 0.05 or 0.01. So you control alpha, you control the extent to which you're going to make a type 1 error. But we got a lot of things that matter that influence power. So we need to talk about those. And we're going to call this section determinants of power. So if we randomly pull a sample that gives us a mean from over here, we will reject the null. If we randomly pull a sample mean and it comes over here, we're going to fail to reject the null. Anything that looks like slop prior to the critical value, any slop that is before the critical value means that we're going to fail to reject the null. Anything after the critical value, that's power. That's our ability to detect differences. So we want to maximize differences, minimize the slop. And here's one way to do it. In this graph, the means are kind of far apart from one another. Here's the critical value. This is the graph I was showing you before. Here's the critical value. All of this red is power. We have more than 50% power because here's mu. So this area right here is probably 10% more of the distribution. So we have more than 50% power. Power is greater than 0.5. Power is written as a proportion. Power is greater than 0.5. And these means are kind of far apart. Let's look and see what happens when the means get together. Look at what happens when we push those means together. So there's barely any difference. So before, it might be, if I'm looking at reading scores of kids who are in first grade and kids who are in fifth grade, I might get mean differences that look like this. Because kids who are in fifth grade read a lot better than kids who are in first grade. But if I'm looking at reading scores for kids who are in kindergarten and kids who are just started first grade, I might get something that looks like this. The means are different, but they're barely different because the kids have not had much of a chance to learn to read yet. These means, when they're close together like that, and all of this is slop over here, when that happens, we have very little power. So in order to maximize power, one thing you can do is maximize mean differences. Let's see. So here's the difference. This has less power, and there's a lot of slop. You can't hardly tell one distribution from the other. All these means under here could belong to either one of these distributions. Here's more power because we've moved, the means are further apart, and now most of this distribution, most of this sampling distribution of means is over here away from this distribution, the first distribution, and we can tell them apart easily. So more power, less power. Now let's think about that in a real life scenario. So like maybe if I was going to go and measure, so let's say I had this really awesome new way of teaching kids to read, and I just know, just because how I developed it, that kids are going to learn to read, and they're going to learn to read well with my technique. So I bring it to the school and I want to try it out, because if I try it out and it works, I can make $1 bazillion off of this, selling this to schools to help kids learn to read. So I'm going to have a group of kids in kindergarten, and some of them I'm going to teach to read using my new technique, and some of them I'm not going to teach to read using my new technique, and then I'm going to compare them. Okay, so in this case, maybe what I did is I went in there and I got these kids and I met with them for 10 minutes every 2 weeks, teaching them to read with my new technique. Now, if I only met with kindergartners 10 minutes every 2 weeks, it doesn't matter what I'm trying to teach them. They're not going to learn much about that. And so there might be an effect. They might have gotten something out of my reading program, but they're not going to get much out of it. But what if I went in there and I taught them for an hour every week, and then on the weekends I also had some kind of program going on where they came and I tutored them for an hour in my technique as well. So now they're getting 2 hours of tutoring in my technique, my new reading technique, a week. Well, then I would expect, if my reading technique actually works, I would expect a lot bigger effect than from the first way, 10 minutes every 2 weeks. I would get a lot bigger effect. I would get kids who could read much better from my tutoring or from my method, my reading method, than kids who didn't get my method at all. So that's how you move mean differences. That's how you pull mean differences apart. You make the intervention a strong intervention. So if you want to give somebody aspirin versus ibuprofen, you make sure that they get enough aspirin, and you make sure they get enough ibuprofen. You don't give them 1/8 of a tablet and then look at the time it takes to relieve headache symptoms. You give them a dose, a good dose, usually multiple doses, so that you can see that as the dose increases, you get better headache relief, faster headache relief, more headache relief, whatever you're looking for. So this is a dose effect. It's like, and it's a dose of my treatment, my reading treatment. So if you want to move mean differences, if you want more power and you want those means to spread out, make sure they get a good dose. Make sure your group gets a good dose of the treatment. And sometimes you can't do that. Sometimes you're looking for mean differences between like men and women on something. Well, you can't give a good dose of maleness or femaleness. You just take people like they are. Or you only have 10 minutes every 2 weeks. The teachers will only allow you 10 minutes every 2 weeks. So you have to be willing to say, okay, well, I only have 10 minutes. I still want to see an effect. So what now can I do? Okay. So remember that the sampling distribution, the shape of this distribution, not the shape in that it's a normal distribution, but the fatness and the skinniness of it, the spread and the not spread of it, depends on sigma sub x bar, which is the variance of the mean, or the standard deviation of the means, which depends on the standard deviation of the raw scores and the square root of n. So the standard deviation of the raw scores spreads this distribution out. It has something to do with how spread out the scores are. Well, it is how spread out the scores are, or how narrow the distribution is. So it has something to do with how wide or how narrow the distribution is. So let's see what happens when we narrow up or widen out this distribution. So here, and remember, we're going after power. Power is our ability to randomly draw a mean from this second distribution and know with a good likelihood that it's not coming from this first distribution. Power is our ability to detect differences that actually exist in the population. So here we go. So I want to show you like what happens when we smush up and spread out this distribution. So here we go. Here's the power we have to detect differences between mu2 and mu1 with the distribution spread out in this way with all this slop. You see how this distribution, if I pick something right here, could be from either one. If I pick something right here, could be from either one. If I pick something right here, only after this critical value will I pick something and call it mu2 and get a significant difference. Say, yeah, I see mu2 is significantly different from mu1, and make the correct decision, because these mu's are different from one another. But I'm only ever going to do it if my sample mean comes from beyond this critical value. So here what I've done is I've reduced sigma. So sigma is now smaller. It's a smaller sigma. Less raw score variability. And now look, here's the critical value, and more than half of this distribution is in the region of rejection. More than half of these means are in the region of rejection. So as sigma decreases, goes down, we get more narrow distributions. These distributions start looking different from one another. Now I can see that they're different. Here's a larger sigma. Here's a smaller sigma, and I can see that most of this one is not slopping over onto, most of the second distribution is not slopping over onto the first when I've narrowed my variance or my standard deviation. Well, n is also part of that formula of the sampling distribution of the mean. So n plays a role in how spread out and how narrow. And this is the one that most people can control most easily. You just increase the sample size. So what happens when you increase the sample size? So here's an n of 10. And remember, anything on top, as it gets smaller, this value gets smaller. So more narrow distribution. As this value gets bigger, this value gets smaller, so more narrow distribution. So I'm starting with a small n, and these distributions are spread out all over one another, and I have very little ability, very little way to reject the null hypothesis. But in this distribution, I've increased n to 1,000, and now the denominator is huge, so this standard error is going to be small, and now I can tell the difference between these distributions. So we have mean differences that affect power. We have standard deviation of the raw scores that affect power. As the standard deviation decreases, power increases. We have the sample size. As the sample size increases, power increases. I forgot to tell you about something that you can do with the standard deviation. So let's say I want to institute my reading, my proposed reading method. And I know it works. I just know it works. So I take it to the school, and with kindergartners as well. And, you know, kindergartners are quite variable in how much they know when they enter kindergarten. Some kindergartners are already reading by the time they enter kindergarten. And some kindergartners don't even know their letters. They don't know anything when they enter kindergarten. They don't know any school stuff. They may know a ton of other stuff, but they don't know school stuff when they enter school. So what if I get up in there in that kindergarten, and I've got kids who are, oh my gosh, they don't know one letter from another. They don't know one single letter yet. And then I have kids that are already reading at a 4th grade level. You see how much variability that is? And now I'm trying to detect differences between what I do and what these kindergartners are already doing. And it's hard to do with that much variability. So one thing we might do to decrease the variability is to just basically eliminate the kindergartners who don't know any of their letters. Eliminate the kindergartners who are reading at a 4th grade level, because the kindergartners who are reading at a 4th grade level are not going to get any better probably with my reading, because I'm trying to help kindergartners. And the kindergartners who don't know their letters are probably not going to benefit from my reading program, because it's not about teaching letters, it's about teaching reading. So let's get rid of those two groups and focus on the regular, just the middle group of kindergartners. Well, when I do that, I narrow up the distribution. So now the distribution is more narrow, and I get something that might look like this, and something where I really can move these kids because they know how to read, they just don't know how to read well, or they're starting to read, and I can help them read even better. And I get a bigger effect, or it looks like it's a bigger effect. It's the same mean difference. It just is giving me more ability to detect a significant difference. Alpha affects power as well. So alpha, if I use alpha 0.05, which is a larger alpha level, I've got 5% in the tail. If I use alpha 0.01, I only have 1% in the tail. Well, all this red region indicates my ability to detect differences, to detect significant differences. Anything outside this critical value, I'm going to call it significant. Well, there's more outside the critical value when alpha is 0.05 than when alpha is 0.01. And so bigger alpha, more power. And that is why people use 0.05 most of the time. Also, the location of this critical region matters. If I put all of my 0.05 in one tail, I have a larger critical region. And if this distribution really is shifted to the right of the second distribution is to the right of the first distribution, and I'm looking on this side, I'm more likely, the critical region is twice as large. than if I divide it into two tails. See, because now here in two tails I got 0.025 over here, I have 0.025 over there, but there's nothing over there for me to detect. So it's all happening over here. So a one-tail test is more powerful than a two-tail test if you choose the right side for the critical region. So here we go. Differences between means. As the differences between means increase, power increases. It moves the distributions apart from one another. We can see that. As sigma, as the standard deviation increases, power decreases. Big old distributions all spread out. You can't tell them apart from one another. As increases, that's the denominator of standard error. As n increases, power increases, because it smushes up, it makes more narrow the sampling distribution. As alpha increases, power increases, because it gives us a bigger critical region. One-tail tests are more powerful compared to two-tail tests. If you put the critical value in the correct tail, one-tail tests are more powerful because you have the entire critical region in one location instead of divided up between two locations. So there you go, study outcomes and power.